Hi everyone. So today I will be talking about quantum computing. Yeah, so here's the agenda. So I'll first talk about the motivation of this talk, and I'll give a very short introduction to quantum mechanics and quantum computing. Then I'll briefly talk about one of the awareness, or one can say superpower of quantum mechanics, which is the non-locality. And then we will talk about quantum theoretical complexity. So this is very closely related to the course that we're taking. And finally, I will go through some classical quantum algorithms. Yeah, so for the introduction. So the goal of this presentation is to explore the power of quantum computing. So during the course of CS5230, we have seen the power of non-determinism, quantifiers, non-uniform computation, or randomization, or interaction, so on and so forth. So what kind of power can the weird and counterintuitive quantum mechanics add to computation process? So this is the central question that we want to answer. And specifically, we will show the following results. We will first define the quantum complexity class BQP. So this is kind of like BPP, is doing some non-deterministic computation with some with high accuracy. So basically, with larger than 1/2 probability of getting it correct, and also doing it in polynomial time. And we will show that this BQP class actually contains BPP. And we will also show that BQP is contained in P space. Well, it's actually an open question whether BQP is whether P space is in BQP. But at least this will give you a rough idea of how powerful a quantum computer is. It could well be that, although no one knows at the moment, that BQP equals to P space. So that means quantum computer is very powerful, much more powerful than we thought. Then after illustrating these central results, we'll go through a few classical quantum algorithms. So for example, Grover's search, Simon's algorithms, and quantum Fourier transform. So I was intending to cover Shor's algorithm, but I think time wouldn't allow me to cover Shor's algorithms. Okay, so to begin, we will need to first know something about quantum mechanics and quantum computing in general. So I'll give a very short introduction. So I think you can all be motivated using the double slit experiments. I think most of you have heard of these double slit experiments. So basically what happens is that, so you have a photon source on the left hand side here, and you have the device that has two very narrow slits. So what happens is that if you only keep one slit open at a time, you will observe that the photon behaves like a particle. So how do you tell that is, so you put a detector on the back of this slit, and you count the number of photons detected. You count the frequency. So this will give you like a Gaussian distribution around the center, behind each slit. So that means the photon is kind of like a small little ball. It goes through the slit and hit the detector. So this is what we expected from classical mechanics. However, if you open both slits, then the detected pattern will be very strange. So first of all, some locations that are not hit when only one of the single slit is open are now hit. So for example, if you look at this location here, So originally, if you only have one slit open, you won't have this peak around the center between the two slits. But right now you will have this this peak, and also the heat count for the original peak here are also decreased. So this actually reminds people of wave mechanics. So for example, if you throw two stones in a pond, if you throw a stone in a pond, it will propagate, the wave will propagate. And if you throw two stones, which is the case here, you will have some kind of interference. Interference pattern is exactly what we're observing here when both of the slits are open. So what does this tell us? This tells us that actually photons are kind of like wave, but how can it be that sometimes it behaves like a particle, sometimes it behaves like a wave? So that has something to do with measurement. So what measurement does is that if you try to measure exactly which slit the photon is actually passing through, so back to this case, if you don't block one of the slit, but rather you just put two detectors at each of the slits, so what happens is that you will have like a double peak pattern, like would you expect if you superpose the patterns here. So what that tells you is that if you don't measure, so basically if you don't measure the location, then it kind of behaves like a wave. But once you measure, we say that the wave function collapses and start to behave like a particle. Okay, so that's enough intuition for now. So we will formulate what we have observed from this experiment exactly using some mathematics. Okay, so here comes the first postulate of quantum mechanics. So everything is a wave until you observe it. So once you observe it, the wave function collapses. So, but what exactly is a wave function? So a wave function is actually some kind of a probability distribution over the configuration of the system. So in this case, the configuration is which way the particle is going. So instead of having like a definite path, we're considering all the different paths that the particle can take, and we'll assign probability amplitude to each. So why do I say probability amplitude? Because notice that the output here is actually complex. It's not a real number. If you take, so the physical meaning of this amplitude is that if you take the square, then you represent the probability density of the system being in that state. So in this case, if you put in x, a particular position for the particle to be detected after the two slits, then you have a probability distribution over the particle's location. Notice that like this probability density does not exist once you observe, or in more mathematical terms, you will collapse into a Dirac delta function where the only possibility is the one that you observe. So this is very subtle, but very crucial to the later on application that we will be looking at. Alright, so the second postulate is that a quantum system can be in a superposition state. So what does that mean? So first of all, we need to know what cats are. So these are, I'm not going to explain it in a super rigorous way, but basically these are objects in the Hilbert space. And then each single this cat represents a certain distribution that can be observed. So in our so in the double slit experiment, these cats could be a direct distribution located at some so for example, this phi 1 can be a direct distribution located at x1, and this would be x2, and you will have you can have a superposition of all of them, you know. So this will be something like this. So anyway, let's go back to it. So if you have two observable states, the system can actually be in a superposition of these two. So let's put a more concrete example. So let's say you have, you know, the first distribution over, you know, the wave function. Oh, okay. So the first wave function is something like this. Actually, I should draw it in, because it can be both positive and negative. And the second wave function is something like this. Each of these can be independently exist, and you can, you know, repeatedly measure it, and then if you plot the measured results, so this will give you basically, you know, the density of the first guy, which is something like this, and then you have the second guy, which is something like this. So each of these is a, you know, physical state that can exist, and you can observe and you can map it out to get the probability density. So what this says is that given these two different states, you can have a superposition state where you have a complex amplitude that sum up to 1, which is written down here. So what this means is that the system can be in the state phi 1 and phi 2 at the same time, but with probability amplitude C1 and C2. So you can think of it like this. So when you try to observe the system like this, you will first select one of the one of the state using this probability C1 and C2, and then you draw sample from, you know, or you perform measurement on phi 1 and phi 2. But of course, you can also add them up directly as well. Yeah, okay. So in general, so this holds for two states, and in general, it holds for, you know, any kind of collection of cats, and more often, very often, we'll talk about like a complete basis. So for example, in the case where the two slit experiments, the complete basis will be, you know, all the Dirac delta for all x, yeah, something like this. And then, of course, if you add up more than two of these basis cat, they also need to normalize it to 1. So the two norms should normalize to 1. Okay. So notice that this superposition has a very interesting consequence, where when you add up two separate wave functions, you are adding in the amplitude, where the probability is, you know, the square of this amplitude. Whereas if you have like a normal probability distribution, so for example, if you have P1 of x and P2 of x, and then we say that, so let's say that the system can be in the P1 distribution in, so let's say C1 plus C2 equals to 1. So we can have a new probability distribution like this. So what this means is that in C1 fraction of the time, you will be in this distribution, and in C2 fraction of the time, you will be in this distribution, P2 distribution. Yeah. So notice that this is very different from this guy, because when you're adding the wave function, but the probability density of the added, the new wave function has this density, which is kind of nonlinear. So compared to this guy. So not only you have like these two terms, which correspond classically to this C1 P1 C2 P2, you also have this interference term. So notice that when you take the norm, because it's complex, you need to multiply the complex conjugate with itself, okay? And then this process will create the interference term. So this is why QM differs from classical probabilities, where the superposition of the state is not really linear. You will create this interference term, which makes the superposition probability larger or smaller than we would expect classically. So because if you look at this term, right? So this term, the interference term, it is exactly something like z plus z conjugate. So what this means is that this term is actually real, and it can be plus or minus. So if you add this term to these two terms, you can be larger or smaller than if you just treat them as probability density and add them up. So this is very important. So that's why also that you have to use complex number, otherwise you as amplitude, otherwise you don't have this interference pattern. Okay. So now let's talk about a very special quantum system, which is called the two-level quantum system. I mean, in general, the cardinality of the set of basis ket is uncountably infinite. So for example, in the case of the double slit experiment, so what we have is something like this. Yeah. So each of these is again like a direct distribution at x. So let's say x0. You will have infinitely many of them to form a complete basis. So in general, the basis ket is uncountably infinite. But however, there actually are quantum systems that have finite and in fact only two basis ket. So this is given by, for example, the quantum spin. So in a spin 1/2 system, you can have spin up and spin down, and there are only two possibilities. So this is actually experimentally shown by the Stern-Gaillard experiment. So what this experiment does is basically it has a furnace that is cooking silver, and then it will emit silver atoms. So because silver atom has a certain magnetic momentum, if you put it through like this magnetic field, you will burn up or down depending on the orientation of the magnet. So for example, so think about this. If you have a classical magnet, something like north-south, let me draw it larger. A classical magnet, north-south. So if you place it, in a certain orientation, then you will receive the magnetic force exerted by this magnetic field, and you will go slightly up or down according to the orientation. By orientation, I mean is in this orientation or this orientation, or So you can have a continuous spectrum of orientation for classical magnet, and depending on this orientation, so you can perhaps parameterize it by this. So you can maybe parameterize by this angle here. So you will get is a continuous spectrum that's detected at this detection screen if you are given a random direction of the magnet. However, so what's actually observed is that there are only two spots here. So what this implies is that there is no continuous spectrum of magnetic moment orientation. There are only two. So specifically, we will call them up and down. Yeah, so this is very strange, but also very useful, because we can treat them as bit. So for example, if you say up is 0 and down is 1, then we have effectively created a qubit. Yeah, so let's go more deeply into the construction of the qubit. So normally the qubit are visualized by the Bloch sphere. So this is the Bloch sphere. So if you look at this, you'll be kind of puzzled, because this Bloch sphere is only parameterized by two parameters, the theta and phi. Whereas if you recall, in quantum mechanics, the wave function amplitude is actually a complex number. So because there are two basis kets, so we should have, we actually need to use four numbers to represent the amplitude. So for example, for the 0 ket, we need to parameterize using C1 and phi 1, and for 1 we use C2 phi 2. So so this one encodes the EI phi term, encodes the complex phase. But however, there are actually only 2 degrees of freedom. That's why we can encode everything we need for a qubit using only 2 real numbers. So the first observation we need to make is that there are actually constraints to these two. Specifically, we need to have, these two have normalizing to 1. The L2 node should normalize it to 1. So because we always have EI phi equals to 1, so we can ignore this term, and we can impose this constraint onto C1 and C2, so this reduces 1 degree of freedom. The second observation we need to make is that the absolute phase here is actually non-measurable. So what this means is that it actually doesn't have any physical significance. So we can only observe the relative phase. So I'm not going to explain this in detail, but basically you can do that through a Hadamard operation. So what this means is that we can parameterize only the relative phase. So this also further reduces down the number of parameters we use. Yeah, let's put this in practice. So because we have this constraint C1 plus C2 equals to 1, so we're only considering the case where, so basically we're considering all the possible probability mass distribution between the cat 0 and cat 1. So it can be, so basically we're interpolating between, probability density fully in 1, C1, that means is, phi equals to 0. In this case, where phi equals to 1. So to do that, we can basically transform things to trigonometry, where we know that cosine and sine equals to 1, and if you use this theta over 2 in taking theta over 0 to pi, you exactly have, when theta equals to 0, you will have 1, 0, which is what we want, and theta equals to pi equals to 0, 1. Geometrically, this will correspond to the latitude in the Bloch sphere. So for example, if theta is 0, then you're at this point. When theta is 1, you'll go to this point. So the theta encodes latitude here, which also is the probability mass distribution between the two cats. So that means if you are at a point that's close to the North Pole, it's more likely that you observe the 0 cat when you take the measurement, compared to if you are in a southern hemisphere, then if you take the measurement, it's more likely that you observe a 1 cat. And the longitude actually encodes the relative phase. So how is this done? So first of all, you plug in the parameterization of C1 here. So you have the cosine theta by 2 and sine theta by 2, and then you can extract the absolute phase, let's say for phi 1. Then you are left with this term with EI phi, where phi is the relative phase. And this will range from 0 to 2 pi. So basically, in the same longitude, you have the same superposition in terms of 0 and 1. In terms of probability mass distribution between 0 and 1. But you will have a different relative phase between the two states. Yeah, specifically, if you are on this point, like on this line, then you have no phase shift between the two states. And as you go along, in the anti-clockwise orientation, you will have more and more relative phase shift between the two states. So yeah, this is what it means by, this is how the Bloch sphere parameterizes a single qubit. So remember, there are only two real numbers that's significant. One is the theta, which is the relative, the mass distribution between the two states, and phi, the relative phase between the two states. Alright, so let's talk about how do you actually combine individual quantum system, because so we've talked about single qubit, but in order to be useful, we need to be able to have multiple qubits. So in general, when you're combining two independent quantum systems, The wave function is the tensor product of the two individual wave functions. So for example, we have the state phi a, and it's expanded in basis this A1, so you have the basis set like this. And here you have a basis set like this, B. When we combine the system, so notice that the new basis is A tensor B. So the cardinality is actually, the product of the two bases, the two individual bases. So this is, I think sometimes people are confusing tensor product with Cartesian. So one useful tool that you can think about is that if you do Cartesian product of the two linear space, so what you will have is something like this, and the cardinality is just the sum of the two subsystems. Compared to the case here where the new system is the product of the previous two systems, so it's much larger than just doing Cartesian product. And actually this is very similar to doing outer product if you look at this term. If you treat this as a vector of Ci and this as a vector of Di, ignoring the basis, then effectively what we will have is a matrix of C1, D1, C2, D1, so on and so forth. C1, D2, so on and so forth. So for our case, when we're considering qubit, so we normally just write, we'll use the shorthand that, when you have, so when you have two single qubit bases and we do the tensor product, we'll just concatenate the base string. So this is a normal practice. So now let's talk about operators. So now we have so record that all quantum states are infinite dimensional vectors. So because this is like a probability distribution or a wave function, so naturally we can define a linear operator on this space. So you have state, and then naturally you will have linear operator or state. So one way to think about it is that, these state are just vectors. So operators, they're just matrix, which encodes linear operation on vectors. In this case, it's the same. You have infinite dimensional vectors, which is an element in Hilbert space, and you have operators that max between linear spaces. So I have this, where you have an input cat, and then it's mapped to a different cat by some linear operation. In quantum mechanics, there are two important types of operators. So the first kind is the Hermitian operator. This is kind of analogous to symmetric matrices. So these are corresponding to observable. So why is symmetric? Because symmetric matrices has real spectrums, and then so each of the eigenvalue is real. And what that means is that it's real, then it can have physical meanings, and so it's associated with some kind of observations. And the expectation of the observable is given by this. Expectation of the observable A under the distribution phi. But we'll be more focused on unitary operators here. So these are quite different from Hermitian operators. So these are kind of complex analogous to orthogonal matrices. So these operators correspond to transformation or evolution of quantum states. Why is that? Is because it preserves the norm. So whereas in this case, for example, if you have A and you have some eigencat of A, let's say phi, so after you apply this eigencat will be scaled by some eigenvalue, and it can be any number. So for example, it can be larger than 1. So what this means is that this thing will take the square, it does no longer equals to 1. Whereas in here, you always preserve the norm. So that means if you do a unitary transformation to a state, and you take the norm, it should still equals to 1. So which means this new state, u of phi, can still be interpreted as a state of the system. Yeah, so let's take an example to make it more concrete. Yeah, let's go over the most classical equation, the Schrödinger equation. So the Schrödinger equation states that the time evolution of the quantum state given by the system Hamiltonian is given by this equation. So normally to simulate this time evolution, we discretize the space, the time, where we can, we can define this time evolution operator, which is unitary as such. So why this is unitary is because if you take, I won't derive it here, but basically it can be derived easily because it's a matrix exponential of a Hermitian. So why this equation satisfy the Schrödinger's equation? So you can just plug it back into the this equation here. So you have so start from the left hand side of the Schrödinger equation, then you're plugging the evolution into phi t, and then you take the derivative, you'll get this term. And you'll get this term because you are taking the derivative with respect to t, and then you get this part out because it's exponential. Yeah, and then you notice that these two terms cancel out perfectly. These two terms cancel out, and you're leaving you with the h, which is the Hamiltonian. Yeah. And this part is just equal to phi t. So in the end, you get h and phi t, which is exactly the right hand side of the Schrödinger equation. Yeah. So this means the time evolution. So what this means is that you can evolve a quantum state to get a state in the future by applying this time evolution operator defined here. So this is an example of a unitary transformation, where in this case you transform a state from t to t0 to t. Yeah, so this actually is a good segue to talk about the original motivation of quantum computing. So why was quantum computing needed in the first place is because if you want to do science, specifically if you want to simulate a quantum system using a classical computer, it will be very expensive. So as illustrated here, so let's say we're interested in simulating a quantum system with n2 level particles. So which we call that two-level quantum system is just qubits. The space dimension will be 2 to the power of n because so let's say you have n qubits. So this exactly is a bit string. So so this is a bit string, and there will be 2 to the power n different possible bit strings. So for example, if n is 2, then you have 0, 0, 0, 1, 1, 0, 1, 1. So you have these 4 states. And for each of them, you will need to have, you need to store this complex amplitude in order to simulate, in order to do anything. So that itself requires exponential space, right? So let's say you just store this as C1, C2, C3, and C4. So that requires exponential space. And what's worse is that the operators, they are of dimension of 2n times 2n, because so any operator, so whether Hermitian or unitary, so it will be like a 2n times 2n matrices here. So for example, if you want to calculate the expected energy, so you will take the Hamiltonian of this system, and then this is how you calculate the energy, which is exactly like something like xt x. Yeah. So we need to store these matrices and doing some kind of matrix multiplication. So as we know that the matrix multiplication has around n square, between n square to n cube complexity. So last time I checked, this is the best matrix vector multiplication time complexity. So if we plug in the size of the system, you will have this complexity, which is 2n to the power of 2.3. So basically exponential time in terms of number of qubits or number of particles. If you want to do time evolution, that's even worse, because as we have seen before, so if you have a Hamiltonian, then you need to, if you want to do time evolution, you need to take the matrix exponential, which is something like I plus h plus h prime, so h square and h cube, where there's also a coefficient for each of these terms. So yeah, it's very expensive if you want to do time evolution. So overall, if you want to do anything, it seems to, if you want to simulate any quantum system on a classical computer, it seems to take exponential time and exponential space. So it's very expensive. And why do we want to simulate a quantum system, you might ask? So this is very important. For example, if you want to do material science, if you want to calculate any properties from the first principle, so for example, if you want to calculate the heat conductivity or even ionization potential of certain atoms, you need to be able to do this simulation to get those numbers from the first principle in the correct manner. Yeah, so this is a very important problem. So that's why quantum computing was proposed as a solution of to counter the hardness of quantum simulation. So if we can have qubits which evolves in a controlled manner, maybe we can perform all these calculations naturally. So that's the original motivation of quantum computing. Yeah, so let's go into more details. like how one can actually do, controlled evolution of qubits. So basically, all we can do is to apply unitary operations on, our qubit configurations. So first note that any permutation matrix is unitary. So this is very easy to prove, so I won't go into the details here. So by permutation, I means permuting the bit string configuration. To put it more concretely, so let's still use the 2-qubit example. So we have these 4 possible configurations. So what we can do is to apply a permutation on it. So this is exactly like if you have the amplitude of C1 to 4, then you can do a permutation, for example, exchanging the amplitude between these two, 1, 0, and 1, 1. And in principle, you can do any kind of permutation as long as it is a permutation. Yeah, so this gives us a lot of different operations. So for example, you can do a single bit flip where you are mapping between these two bits. You're exchanging the amplitude between these two bit strings. So, where the ith qubit is 0 and ith qubit is 1. Yeah. And you can exchange 2 bits. So for example, for the ijth bit, you can just exchange whatever the value they have. To put this more concretely, let's just go through this more slowly. So if you have like B1, BI, BJ, and 0, 0, 0, 1, 1, 0, 1, 1. So after this mapping, in the original ith column and jth column, okay, so let's call it ith column, jth column. So we have 0, 0, and 1, 0, and 0, 1, and 1, 1 here. So this is what it means. Also, you can have what's called a controlled NOT gate. So this is very useful. So you can implement it by exchanging these 2 configurations. So where the ith bit is 1, and then you exchange the configuration where the jth bit is 0 and 1. So notice that this is equivalent to mapping this bit string to this bit string. So how is that? So so if B1 BI is 0, then this does nothing. Yeah, so you only need to consider the case where BI is 1. So if BI is 1, then it effectively just flip the BJ bit. So because 1 plus 1 here is 0, and the 1 plus 0 here is 1, so you're effectively just flipping the jth bit. So when the ith bit is 1. So this is exactly what we have done here. Also, you can do a bitwise AND. So this is kind of similar to the above, the C0 gate, where you're exchanging these 2 configurations. So the I and jth bit, when they're both 1, right? Then you exchange the case where the kth bit is 0 and 1. So yeah, so this is equivalent to mapping to adding the kth bit with BI and BJ. Yeah, so notice that this is a very quintessential kind of quantum gates. So because we are only allowed to do unitary operation, and unitary operation are reversible because we have this. That means no matter what you do, you cannot just erase a qubit. So what you can do when you want to perform some logical operation is to do something like this, where you store the output into some other register or other qubits. So this will make sure that the whole operation is reversible, because so if you want to go back from this to this, right? So you can just add bi to this position again, then you will get back you will get back this configuration. The same can be done here. So if you have done the bitwise AND or Toffoli gate, you can take the N of I and J and add BI and BJ here. So then you can recover the original string. So everything is reversible here. Yeah, so besides permutation, you can also do rotation, because any rotation matrix is also unitary. So what we can do is that we can rotate. So let's say this qubit is in this state phi. We can rotate this in any axis. So for example, we can rotate it around y-axis. So this is effectively, keeping the phase, keeping the relative phase fixed by you're changing the probability amplitude between 0 and 1. You can also rotate it around the x-axis. So doing this will be changing, changing theta and phi at the same time. Or you can just do, rotate around the z-axis, to just change the phase, relative phase. So there is a very special operation which is used again and again, which is called the Hadamard operator. So which we'll use quite a bit when we go into the quantum algorithms like reverse search and so on and so forth. So this is done by, this can be constructed by two axial rotation, where you first rotate around y-axis by 90 degrees, and then you rotate around rx by 180 degrees. So what this does is to create equal superposition. So what this means, okay, briefly. So we have this matrix. So if we are in the state of, so this is basically the 0 state, and then all we get is 1, 1 here. So this is the equal superposition between 0 and 1. So whereas if you plug in, the other basis cat, what we get is 1 minus 1, which is 0 minus 1, this state. So notice that in both the cases, you'll be, you have 1/2 probability of being in 0 and 1 state. And the only difference between these two states is the relative phase. So here you have +1, here you have -1. Yeah. So if you go back to the block sphere, so what this means is that the Hadamard gate will map this 0th qubit to this point, and the 1 cat to this point. So what this does is to create what's so-called equal superposition. And this is very useful when you are trying to, do quantum algorithms, because effectively, if you have equal superposition, let's say in all the input state, so let's say you have 2 qubits, and then you have the equal superposition as such. Then if you perform any kind of bitwise operation here, it's kind of like you're trying out all different inputs. By all different inputs, I mean like all these 4 states. You're doing calculation on all of them. So yeah, this is kind of like a common intuition why quantum computer is different, is because you can compute for all these different inputs in parallel. It's kind of like NP, where you actually try out all these different certificates. But notice that it's not that simple as just doing all these possible input at once, because in the end you can't retrieve the output exactly. You have a superposition of all these states, and when you do measurement, you can only retrieve a little bit of information out of this. So yeah, that's the catch. So you can highly parallelize your algorithms, but because you can only get your output through measurement, and that's also probabilistic, it's not very efficient to get information out of this superposition state. Okay, yeah, so let's move on. So one may ask, there are many different so what you just described is these gates, they only operate on a few qubits. In fact, only at most 3 qubits. I mean, the biggest one is the Toffoli gate. Whereas in general, if you want to do any computation on n qubit state, you will need to apply the n qubit or 2n by 2n unitary operation. So there is this nice theorem proved by Deutscher that actually states that you only need these 3, at most 3 qubit gates in order to perform any arbitrary unitary operation on n bits. So this is a very nice theorem. So that means we can build circuits like we did in classical logic, where you only have like two bit gates, but you can perform computation on n bit input. In this case, it was proven that if you have a set of Hadamard gates, Toffoli and phase shift gates, you can build any d qubit unitary operation up to approximation error. So we'll call these 3 the elementary quantum operations. All right, let's go into the first power that quantum system can have. This is actually kind of different from doing the actual computation, but rather how information are stored. So we'll say 2 systems are independent if we can write the combined state as a product state. So for example, this uniform superposition state, so we can write them as such, whereas as a product, the 2 single qubit superposition in equal superpositions. However, there are states that cannot be written as such, and we'll call them entangled. So here is an example. So you have 0 plus 1 1. So it cannot be written as a product state. So you can simply do some calculation to find that there's no way that you can write it into a product. There's no way that you can find the solution of so if it can be written as a product state, then that means it's equal to C0 D0 first qubit times C1 D1 and on the second qubit. So yeah, you can easily deduce that this is not possible. So this state is not independent. So what's the use of this entangled system? Is this kind of system can exhibit non-locality. So which is what kind? So there's a famous paper by Einstein called proposed so-called EPR paradox, which kind of talk about this phenomena where the information can transmit instantaneously through a highly physically separated system. So what this means? Okay, so because the system is entangled in this state, there are only two possible observations. You either get 0, 0 or 1, 1. So that means if you measure the first qubit, you already know the second, because the second qubit is always the same as the first qubit. So even if the two qubits are separated physically very far apart, so let's say light years apart, if you just measure the first qubit, you instantly know what's the content of the second qubit. So this is called the non-locality of entangled quantum system. And this is very unique because most of the physics law that we have is local. The light and sound travel at finite speed, and yeah. So this is very unique. So actually, you can explore this non-locality of quantum system in the following way. Yeah. So the so-called parity again. Suppose you have two players, Alice and Bob, who are physically separated. Then you have the following protocol or game. So you first randomly choose X and Y, you give X to Alice and Y to Bob. Alice and Bob has to return 2 bits, A and B, and they wins if the bits are different when X equals to Y equals to 1. X and Y are both 1. And if this is not the case, they need to return the same bit. Yeah, so just look at this for a moment. We can actually prove that Alice and Bob can win. They cannot win, or they cannot come up with a strategy that wins with probability of more than 3/4. So why is that? So if you look at all the possible states of X and Y, so basically you need to have different bits in this scenario and the same bit in all the other scenarios in order to win. So win condition. So what Alice and Bob can do is basically So let's just talk about the deterministic case here. So because they only have the local information X and Y, so we can basically encode their strategy as AX and BY. So basically that's their strategy. So assuming we were doing deterministic computation. So basically this can only have, we only have 4 different different maps here. Whether it's identity map, so this just returns X and Y, or it flips the Y X bit, and it flips the Y bit, or it flip both. Yeah, so basically you can calculate the win rates here. You can find that no matter what you do, you can only you can only have so all these 4 maps, they create 2 outputs that's the same bit and 2 outputs that's with different bits. So no matter what you do, you can never produce this pattern exactly. because you always produce 2 same bits and 2 different bits. So there will always be one mismatch between these different bits and the same bits in a win condition. So that's why you can, no matter what you do, you can win only 3/4 of the time. And probabilistic strategy won't help here, because in order to be on average win more than 3/4, that means at least one of this map here need to have the win rate larger than this, which is not the case. Right. Yeah, so here's the detailed proof, which I've already gone over. So if you have quantum information, then it's a totally different story. Then we can win with probability more than 3/4. Okay, so let's see how it's done. So as before, we prepare this entangled state. This is often called the EPR state, because it exhibits entanglement. So Alice and Bob prepare this EPR state, and they each take 1 qubit. So let's say Alice take the first qubit and Bob take the second qubit. And then the game proceeds as normal. You choose the X and Y and give X to Alice and Y to Bob. So now Alice and Bob does additional step here. So if Alice receives X and she check that X equals to 1, she will apply this RY rotation to a qubit, and Bob does the same but with a different rotation angle here if Y is 1, and then they perform a measurement. Okay, they perform a measurement, so they will get their qubit with they observe their qubit with certain probability distribution. And then they'll get A and B from these 2 qubits. So basically, you have A and B qubits, and that will be their output. All right. So how is this different? So first of all, if X and Y are indeed 0, they haven't done anything, then the qubits are still in the entangled state. Right. So this is the first case. So basically, they will always get A and B. Yeah. So they will always win, because in this case you need to output the same bits. In this case, in case 2, where only one of the bit is 1, they will actually win with probability of more than 0.85. Yeah, so in this case, because X is not equals to Y, the win condition is still outputting the same bit. In the last case, where X and Y are both 1, they need to output a different bit, and so in this case they can win with probability of 1/2. So overall, their win rate is 0.8 if you add up all the odds. Yeah. So which is larger than 3/4. Yeah. So this is achieved because they can have they can perform some local transformation, whereas their local transformation will actually alter the state that the other one have. Okay, so how does this work? So in the case 2, we only want them rotate their qubit, because there is a rotation by it's a rotation by pi/8. So effectively, if you do the calculation, you will get this probability. So you will get the same qubit with this probability. If they both rotate, then it's very interesting. So if you both rotate, if you calculate the whole thing, you'll get that they will transform the state into a uniform superposition. So yeah, so rotating once and both rotating has different nonlinear consequences. I think that's the key here. So in this case, because it's all in equal superposition, so the qubit with the same output, same bit, will be these two, which has one half probability, and these two will occur with also 1/2 probability. Yeah, so this shows that quantum information is indeed something that gives you an edge in this case. This will give you a strategy that communicates something. Yeah. So the key here is that this game is all about communication, because if, let's say in the classical case, if Alice and Bob can talk to each other, then they can win with 100% 100% win rate, because they only, so basically if they can talk to each other, then they both know what X and Y is, then they can just communicate to see whether they need to perform output same bit or different bits. So this 3/4 actually kind of denotes the no information win rate. The fact that you can win this with this entangled qubit means you can actually transmit some kind of information through this entangled qubits. So yeah, so I think that's very cool. Okay, so now let's go into the main topic, the quantum complexity. So here we have we first need to define our framework for performing quantum computation. So how is it actually done? So here I'm going to define a framework for computing Boolean function f on input x on an m qubit quantum computer, using what we have defined, qubits and unitary operations. So first, given this f and the input length, we use a classical computer or Turing machine to compute a description of the series elementary quantum operations U1 to UTN. So and then we initialize our register such that the first n bit contains the input, and then we'll apply U1 to UTN sequentially. So in the end, we'll perform a measurement of the register. We'll get a length of n bit string, and then we'll output B1. So for example, so assuming that we're doing a decision problem. So note that this is kind of like a randomized computation, but as we have explained before, this is different because all this complex coefficient stuff. So then we can finally define BQP. So if we given first we'll define the Q time. A Boolean function is said to be computable in Q time of Tn, where T is some function, if there is an efficient classical Tm that can compute the description of all these elementary quantum operations, and such that if you perform this protocol here, you can successfully compute X with at least 2/3 probability. So this is similar to a BPP here. Yeah, so a Boolean function is in BQP if it's in Q-time poly. Yeah. So basically, efficient probabilistic quantum computation. error bounded quantum computation. Yeah, so right now, okay, so let's show that BPP is containing BQP. So the first proof of lemma, which says we can implement any classical Boolean circuit with quantum circuit. Quantum circuit is nothing but this guy, a series of elementary quantum operation, and recall that elementary means less than 3 qubits. Yeah, so how can we do that? So it's actually very simple. So if you are given a Boolean circuit of size S, yeah, so first thing you need to do is to come out with the equivalent quantum circuit where you replace the N or the not by its quantum analog. Yeah, so basically we have seen that this can be done by a Toffoli gate. This can be done by C0, right? And this can be implemented through De Morgan's law by inverting the OR with into AND. Yeah, so you can come up with this quantum circuit. Let's denote it just by F. Okay. So the first thing you do is to construct your quantum circuit as such, just by going through the each Boolean gates, and then you run the following protocol. Okay. So notice that we will need this many qubits, S plus 2m plus n, and we see why. So you first initialize the first n bit. So this x is the n qubit input. So you encode the input into the first n qubit. Then you will run your equivalent quantum circuit here. And then you will store your output into this n bit. So you have the first n bit, and you have this n bit here where you store the output. And you also need to use S bit here, as one for each gate, because there are S number of gates. Because recall that for all these operations you will require additional scratch memory in order to make everything reversible. So yeah, you write, you use the scratch memory in the back using S bit. So then you need to get rid of this, because you can't measure it right now to get fx, because this z bit is kind of random. You can have some kind of superposition in the z bit. What we want is that we in the end we get we clear out the back, such that when we measure the string, we'll exactly just get x and fx, where x is fixed and fx is your output. So we don't want any other random sources. Yeah, so how do we do that? So we can copy the n output qubit to this space we have left, the nth bit output space. So we copy it here. So this can be done using C0. And now we can run all the gates in reverse. I mean, here we don't need to translate the circuit again. You just need to run the circuit in reverse, and this is possible because all the quantum gates are reversible. Recall that they are all just unitary operation. So if you do that, then you basically changing this first n plus n bit back to the original state, where the first n bit is the input and this n bit is clearing. The output qubits here will be cleared, and also you have cleared the scratch space at the back. Okay. Yeah. So this is exactly what we want, and you can just measure the output state, and then you get this portion, then you'll obtain a sum of x. Yeah, so note that this algorithm is completely deterministic because you are only, this is the only state you're given. Fx is the only state that's left in the final, after all these transformations. So if you measure it, you will 100% get fx. Yeah, so this shows that you can implement any Boolean circuit with a quantum circuit. And what's left is very simple because, so first of all, we can, so although this is completely deterministic, you can easily add in randomness by applying Hardeman gate. So for example, if you apply Hardeman gate to a 0 qubit, you're creating this superposition, and the measurement will give you like 50% 0 or 50% 1. So this is exactly like a coin toss. So yeah, it's very easy to do a coin toss using a quantum circuit. Plus, we have already showed that p-poly is in BQP. Since p-poly also contains BPP, this is a known result we have shown in the lecture notes. Then we have proved that BPP is actually in BQP. Yeah, so that concludes the first part of the complexity analysis. All right, so let's look at the second piece. BQP equals to, BQP is contained in P space. Yeah, so recall that I have said previously that to simulate any quantum system, you need exponential many space. So actually, that's both correct and incorrect. So here I'm quoting the Nielsen Chen here. So in terms of quantum computational complexity, so the Schrödinger picture, which is what we have been using previously, leads to exponential space simulation. Exactly because of the reason that I gave. On the other hand, if you use Feynman's path integral, you can do that in polynomial space. So, and that is what we're going to prove here. To simulate this BQP computation, we only need polynomial space. Yeah. So how to do this, path integral calculation? So suppose we are working with n qubit here, and f is computable in BQP. So right now we want to simulate this using classical computers. First we, if we fix any output string y, then the probability of getting this measurement is given by this. So you first have a initialized state into all 0 qubits, and you apply all the quantum gates from 1 to t, and then you take the inner product between this output and the final state. Yeah. So what we can do is that we can insert the so-called completeness relation. So if you have a complete basis here, so for example, in the case where you take xi to be all possible n-bit strings, you have these relations, and then you can plug in between each gates, and then what you get is this sum where you will get this sum where each term of this sum is a fixed choice of x1 to xtn. So it's kind of like a path, and there are many each term in the sum is a path, and the path is defined through these choices of xi's. And this will simplify, this will reduce our space requirement for simulating the quantum system as such, okay? So notice that we only need to so because this is a sum here, we can compute them one by one. So that's the key. We can compute them one by one, and after this whole computation, we can erase whatever memory we have used and just store the the product of all these individual terms here. So do the calculation for the whole path, and then you can erase your working memory. So right now, okay. So then the key is to see how much memory does this each computation cost. So if you fix a path, okay. So if you fix a path from 1 to n, you only need to compute this tn many terms of this guy. So how much space does each of these takes? Well, this take a times a plus a bit to compute, because this u I minus 1 is elementary unitary operation, so it's at most 2 to the 3 by 2 to the 3, so a times a here. And we only need to store the relevant a bit from x I minus 1 and xi here. Yeah, so it's actually 2 times a. But anyway, it's a constant to compute these terms. So in the end, you have something like a c times tn many space needed for each path, which is a polynomial because t is polynomial. So the whole thing just take polynomial space to compute, because so you can just start by iterating through all the different paths. Yeah, so you enumerate paths, which is x1 to xtn, and for each of this path, this takes a polynomial space. Yeah, so then you just calculate the term, this sum, this product term here, and you store it, and then you move on to the next path, where you can just clear all the memory used for the previous path. Yeah, so that concludes the proof. It only takes a polynomial space for calculation. However, this still takes exponential time because there are exponentially many such paths. So yeah, exponential time is still unavoidable, and simulating quantum system or classical computer is still hard, even if you use the path integral formulation. Yeah, so here are some open question in the quantum complexity theory. So, for example, we don't know if BPP is equal to BQP, and we don't know whether what's the relationship between NP and BQP. And furthermore, we don't know that if P space is in BQP. We know that BQP is in P space, but it's not known that whether this is true. I mean, if this is true, then we will have P space equals to BQP. I think this will have huge implication, because you can solve arbitrary hard problem that as long as it takes polynomial space, and then you can solve it efficiently in polynomial time using quantum computer. I think that will have huge implication. Okay, we'll take a rest before we go into quantum algorithms.